Okay, my name is Rachel, and we're all here for calculus. Maybe we could go around the room and have everybody just kind of introduce me. I'm going to try to match a face with the name. And you might have to actually speak up because the microphone is I think near the front. Like, so say it like you really mean it. Julia? I'm sorry, I didn't catch the one in, the person in the back. Great. Great. So as I said before, I'm Rachel, and you can call me Rachel. I wanted to spend a few minutes just going over some of the syllabus stuff. Now, everybody can read, so I expect you to read through the syllabus. I'm just going to kind of point out some of the more salient details. One of the things I want to draw your attention to is a resource. I assign practice exercises that I don't collect for a grade. Usually it's really obvious when I'm assigning something that you're going to turn in, like there'll be a big due date on it. That's your first clue. So we have in-class quizzes, and we have problem sets that are assignments that you'll turn back, and there'll be a due date on those. But the practice exercises are just, for practice. They're to help make sure that you're prepared for the assessments that are coming up. And in the ones that come from the text, now this very first chapter that we're covering, the practice exercises are coming from a different text. But once we get into the second chapter of our notes, the practice exercises all come from this Larson text. And there's an online resource called calcchat.com, and I think there actually is chat help, but I'm pointing it out not for the chat help, but because there's solutions to most of the odd-numbered problems, and I assign odds because I want you to be able to check your work. The answers are in the back of the book, right, just the answers, but the calcchat.com will have actually worked out solutions. And, they're not perfect in that there might be some steps missing. You might wonder how'd they get from this step to that step, but usually it's often a good, at least gives you an idea of how they approach the problem if you're stuck on a problem. I hope everybody will have access to a TI-83 or 84 calculator, or possibly an NSpire that doesn't have a computer algebra system on it. There are different models of the NSpire. The rule is that you just can't use a calculator that has a computer algebra system on it for quizzes and tests. So the TI-89 or the NSpire CAS, those are verboten. But the 83 or 84 calculator, in fact, students have taken this course just fine with a scientific calculator. But sometimes there might be moments when you'll wish you had a graphing calculator. In this course, what we do is we study functions and how they change. That's basically, and then, some other things. But the basic idea behind calculus is the study of functions that can change and how they change. We begin the course with some analytic geometry, which doesn't require any calculus at all. It's a lot of algebra and connecting how a function, how an equation looks with its behavior in the graph, which I think kind of primes us nicely for the types of things that we do when we start looking at the derivative of a function. And then we go and spend some time on derivatives, and we spend some time on integrals, which is sort of a basic Calc 1 type material. We have a quiz every week, most weeks anyway. I don't give a quiz in the week that we have a test, obviously, but these quizzes are short. They're 3 or 4 questions. They're intended to just help us keep up with the material and let us know early on if we're struggling with some topics. As I mentioned before, there's problem sets. The problem sets are collected and graded. I post the problem sets to Canvas. You might get a hard copy handed out in class. but there's like a big due date on it, so it's usually pretty clear when you're handed something that you're expected to turn in. And then we'll have 5 tests and a comprehensive final exam. So if you miss a quiz or a test ever, you should be in touch with me and Ms. Morgan Puglisi as soon as possible, ahead of time if possible. Like if you know, like I'm not going to make it in, I should get a text from you. My cell number is up here. Feel free to text questions also if you're just struggling, with a problem, you can't figure it out. Like people text me. Sometimes they'll send me a photo, like a picture of like where they're at and where they're stuck, and I can also like give kind of feedback or a little nudge in the right direction. But also, if you're going to miss a quiz or a test, you have to be proactive about that. Let's see. So your grade, I'm going to talk about how your work is graded in just a moment, but your final grade is computed. The quizzes are just 10%, 35% for the problem sets. Your tests are worth 40%, and the final exam itself is worth 15%. If you have questions on how your grade is calculated at any point, just let me know, but they're just based on these weighted categories. There is help for this class. As I mentioned before, you can text me. You could also email me. You could call me, or we could set up a Zoom session. I'm sure there's some resources available to you right in your school to get some help with this material. Everybody has this academic integrity contract, and I'm going to just take a few minutes to talk about that. I think that if you were teaching a course and you wanted to come up with a set of ground rules for what's allowed and what's not allowed, you'd probably come up with something similar. I don't think there's anything like too unexpected that shows up in here, but on practice exercises, please work together, get help. I would expect some of them are hard. I would expect that you might need help, and you should get that help. On problem sets, please, if you want, work together, ask questions, get help. The stuff that you could take home, I'm expecting that you might avail yourself of notes and resources that you have, as long as the solution that you turn in accurately reflects your understanding of the problem. Like if that understanding came after getting help, fine, that's great. That's how learning works. I want to make sure that when you get help on a problem, it's not just to get a solution down, it's because you're actually understanding how the problem works and why that solution is the solution. Quizzes and tests are done independently. They're on occasion, sometimes I have assigned a take-home quiz, and those have the same rules as any other take-home assignment, but the in-class assessments are done independently. It's okay to ask questions if you need clarification. If you're not sure what you're being asked to do, or you're not sure what information's given, you can ask those types of questions. As I mentioned before, you can use a calculator that doesn't have a computer algebra system. You can't use a phone or an iPod or anything that can run apps or connect to the internet. You can't use you can't use your notes on in-class assessments. And then everything that we have, I don't think you probably haven't activated your accounts yet, but once you activate your accounts, our course has a home on Canvas, which is kind of like Moodle, kind of like Google Classroom. Like it's just a place for a place for our classes to like, so I could post materials and stuff. So right now, this is the syllabus page, this is the home page. Probably after today, I might change the home page, but there's this menu of items here on the left-hand side. You can see that syllabus is highlighted there, or bolded. So this is just the same thing that's on the printed out document that you have. Pretty soon, I'm going to change the home page down here to modules. When you log into Canvas, you should make sure that you keep your credentials secure to yourself so nobody else can log in as yourself. That's part of the academic integrity. There's a spot here for you to sign the academic integrity contract. It takes like 2 clicks. It'll just take you a few seconds. So after you've activated your account, and after you've read that academic integrity standards document, just click here and say, yes, I agree to follow the rules. Did it go entirely? Huh, that's weird because I'm using earbuds, so, well, okay, because there's no sound coming from, like, the only sound that I'm getting out is in my earbuds, I'm pretty sure, so. Let me see, maybe I could boost the gain. Oh, okay, all right, cool. There's another document when you might notice here, it says guidelines for submitting assignments online. I would expect that when you submit, when you turn in your problem sets, a lot of the time you'll just hand them in class. Miss Morgan Puglisi will scan them and send them to me. But if you, for some reason, are gone one day when something's due, if you're absent when an assignment's due, that doesn't give you an automatic extension on the assignment. It is up to you to turn these in. Or maybe you forget it at home when it's due, and you're like, oh no, I need to turn it in. You still can do that. If you have access to a smartphone or some kind of device like that, there's instructions on some apps you can use to create like a scanner, kind of a PDF of that document, and there's instructions located there for how to do that. There's also a link with practice tests. These are practice tests for the whole semester. Like, as I mentioned, we're going to have 5 tests and a comprehensive final exam. So you'll note there's practice tests and solutions to all of those. So as we kind of work through material, we're getting ready for a test, just click on the link for the practice tests, and you can, give yourself an opportunity to, just practice a variety of problems and also see my solutions, how I work them out. As we go through the course, I'll build a little module for each topic, for each chapter. And so you notice there's one here already for plane analytic geometry. I've got a PDF for the practice exercises, and also there's a little link for today. And what I do is I create a page for each class day, and if you click on it, you'll notice it lists what we're doing. This is just exactly what I've got listed, here on the first page of the OneNote document. And then there's also an empty spot for notes and for videos. So we fill out these notes kind of together, and I'll save a PDF and post that to Canvas. Also, I'm recording what we're doing right now. I'm recording the screen, just recording the screen and the audio. There'll be a link for a video, and usually that takes longer. So the notes usually will be up maybe shortly after class. The video I have to edit and render, and so that's usually up by the following day. So if you miss a class, or if you just want to review something that we did, there's opportunities, resources there for you to do that. Okay. Just a little note about, trying to make sure that we're present in class, like mentally present. When you're physically present, please be mentally present. Please don't be chatting. If you have a question, please just direct it at me, and that way everybody can hear the question and the answer. I don't know if cell phones are an issue in your school, but they are up here sometimes, so I'll just remind us all to have the ringers off and make sure that we're not being distracted by phones vibrating. Let's see. So the next thing I'll do is just talk a little bit about how your work is graded. So I grade your work holistically. I don't just look to see if you have a right or wrong answer. In some ways, the answer is sort of tangential to what we're getting at here when we work out these problems. So when you write out a solution to a problem, I evaluate your solution based on these 3 criteria. I see whether it's well executed, whether it's well communicated, and if it's essentially correct. And I've sort of described what each of these things means. And as I am looking over your solutions, I just put it in one of these bins, right? I look to see, is it A-level work, which gets a 5? Is it B-level work, which gets a 4? Is it C-level work, and so on? And if it's A-level work, I just call it 100%. I don't kind of make distinctions between whether something should be a 95 or 100. If it's A-level work, it's A-level work, it all gets 100. If something's B-level work, it all gets 87%, and so on, right? So a C is at 75%, a D is at 60%, and F is at 40%. It is possible to get a 0 if you leave something blank, or if you kind of just completely miss the mark on what the problem's asking you to do, like that might get a 0. You'll notice that this scale is not linear. You know, from 100 to 87 is 13 points, and then 87 to 75 is 12 points, and then 75 to 60 is 15 points, and so on. So it's not a linear scale. I'm going to talk about that in just a moment. When you get something back, you'll have this grade sheet on it, like a grading cover sheet, basically, when you get something back. So you'll see there's a box for each problem. And then next to it is a little ×1 or ×2, and that's the weight of each problem. So problems that are longer or maybe harder or a little bit more involved might be a ×2 problem. And when you get one of these back, you'll have these you'll see this grade sheet, and then maybe on the first problem you got a 5 and it was really well communicated. On the next one you got a 5 and it was maybe a little bit less well communicated, but still pretty good enough to be a 5. And you got a 4. Maybe you got a 3 on this one, and you really need to work on the communication there, and maybe a 4 on this one. So you'll notice that there's been a number circled and an indication of how your communication was. The communication is not like a separate grade, not a separate part of the grade. It's one of those 3 criteria. It's just of those 3 criteria, it's the one that people often have a harder time figuring out where they stood. So that's just extra information. Like how you did in the communication is sort of all rolled into that numerical score. So I take each of these scores, I multiply it by the weight. So this would be a 5, a 5, a 4, this would be a 6, and an 8. I add these up to get the total number of grade points. So 10, 20, 28. And at 28 grade points, I go over to this table, and as it turns out, that's an 87%. So that's how I go from your grade points to the percentage. I'm going to explain how I make this table, not because I need you to explain it back to me, but just in the interest of being transparent about how I get your numerical score at the end. If I'm going to go back to this page, if somebody got a 5 on everything, on each problem, you would expect that they get 100%. So if somebody got a 5 on everything here, it would add up to 35 grade points, and that's why 35 grade points is aligned to 100%. If somebody got a 4 on everything, you'd expect them to get an 87%. And if somebody got a 4 on everything, that would add up to 28 grade points. So that's why 28 is aligned at 87%. And so on. If somebody got a 3 on everything, that would be 21 grade points. If somebody got a 2 on everything, that would be 14 grade points here. And then in between, it's linear. So I just go down by the same amount from 100 to 87 over however many grade points that is, 7 grade points. So in between, it's linear. Are there questions so far on like what to expect and how things are going to go? Okay. All right. In that case, maybe we'll get down to the fun part. We'll start working through some of this analytic geometry material. We're just going to go through this first section, get through some basic definitions. Some of the stuff in this first chapter is stuff you may have seen, like, maybe you're no stranger to the distance formula, but we're just going to kind of connect these geometric ideas with their algebraic equations. and do some stuff. Some stuff may be less familiar to us. But if I have the coordinates of 2 points in the plane, we'll call one of them x1, y1, and the other one is x2, y2. We can get the distance, like the straight line distance between those 2 points by using this formula. I am not a fan of memorizing formulas. You can memorize this formula if you like. Sometimes I use it so much that I just memorize it even if I don't want to. But this formula is easily derived. So what I'm going to do is I'm going to pick a point, say, over here. I'll call this x1, y1. And then I'll pick a point maybe up here. I'll call this x2, y2. And so we want to figure out, what's the distance, that straight line distance. And what we're going to do to help us with that is one of our favorite things to do in the plane, which is draw some perpendiculars. So I'm going to draw this line going straight out this way, this horizontal line. I'm going to draw this vertical line going straight down. And the one is perfectly horizontal, one is perfectly vertical. That means that where they meet here is a right angle. And so what we've constructed now is a right triangle. What we need to figure out first is, what's the coordinates of this point in the corner where those two perpendiculars meet? What is the x coordinate? Say it loud. 6. Oh, okay. So 1, 2, 3. So so we don't know what the scale is here. It's x2. It has to be the same as the point straight above it. What about the y coordinate? y1. That has to be the same y coordinate as the point directly to its left. Great. So now we have these coordinates. Let's figure out what these distances are. How do I get a vertical distance? Like, if I had a couple of points, say this was the point 2, 5, and this was the point 2, I don't know, -1. How would I figure out what that straight line, I know it looks a little slanty, but imagine that that's perfectly vertical. What should that distance be? Say that again? Or I don't know, it seems like I heard somebody maybe suggest a result here. 6. Why 6? Right. Yeah, so this whole, another way to put that, and that will help generalize it, right? So you're saying I got the 5 to get to the y-axis, or the x-axis, and then an additional 1 to go down 1 unit below. So another way to kind of put that is I just did some subtraction. I did the top minus the bottom. And that's 5 minus a -1, right? And that gives us +6. And that's generally how we always get a vertical distance. You're the top y minus the bottom y. And if we do that here on the left, that gives us the expression y2 minus y1. Now, what about a horizontal distance? Like if I'm going to go back over here on the right, suppose I have this point here which is like negative 3 comma -1, right? So it's the same y coordinate, which means that's going to be perfectly horizontal. What would that distance be? Yeah, can you tell me how you got that? Yeah, great. So a horizontal distance we're going to get by taking the right x-coordinate minus the left x-coordinate. So down on the left here, that's going to look like x2 minus x1. Okay, so now, look, we have this right triangle over here. And what we want is an expression for the distance, d. So Pythagoras says that if I add the squares of the two legs, I'll get the square of the hypotenuse. So Pythagoras tells us that d squared is x2 minus x1 squared plus y2 minus y1 squared. And then if I want to get d by itself, what do? Take the square root, yeah. So d is the square root of x2 minus x1 squared plus y2 minus y1 squared. Hey, I've got these squares inside a square root. Can I just say that do those just cancel each other out, like the squares and the radical? No, they don't. Can anybody tell me why? Yeah, because of the addition inside. Right, so we can't distribute a radical over addition or subtraction. So this radical stays, right? That's the simplest form. Great. Let's do an example. If ever I get excited sometimes, and I'm always ready to kind of like for the next thing. So if I ever like move on and you're still writing from the previous page, just give a holler and let me know that I should go back. I'm happy to do that. So in this example, they just want us to find the distance between these 2 points. So the first thing I'm going to do is I'm going to write down that distance formula. One of these points has to be my x1, y1, and one of these points has to be my x2, y2. It really doesn't matter which is which. I just label them so that I keep them straight. So I'll just take the first one as x1, y1, the second one is x2, y2, and now we can plug stuff in. So x2 minus x1 is -1 minus 3 squared plus y2 minus y1 is -5 minus a -2, so that's +2 squared. And now we simplify. So we've got -4 squared plus -3 squared. 16 plus 9 is 25, so we get 5. Here we did it just by plugging in the actual formula that we needed. If you're ever unsure, you can't remember exactly how the formula goes on a problem like this, it's not a bad idea to just plot the points. Whoops, that's a circle. So you could just plot the points. 3, -2, and -1, 5. We're looking for this, and then you could just draw those perpendiculars. Make your own right triangle, and find the lengths of each of these legs. and use Pythagoras to find that. So if you're ever unsure, you can kind of follow your nose through the process just by plotting the points. Are there questions on that example? Okay. So next, the slope of a line. This I know you've seen many times, right? So change in y's over change in x, or rise over run. I misspell the word rise on purpose to make sure we understand that the y's go on top. So we can find the slope of a line connecting these 2 points. I'm not going to, belabor this process too much because I think we've probably done it a whole bunch. But y2 minus 1, again, I need one of my points to be x1, y1. The other point is going to be x2, y2. Doesn't matter which is which as long as we're consistent. Y2 minus y1, negative 7 minus a negative 5, so that's plus 5. And then x2 minus x1, negative 2 minus 3. Do some arithmetic. We end up with negative 2 over negative 5, and then simplifying that is a positive 2/5. So it's a positive slope. That means it will be rising as x moves from left to right. Not terribly steep, only 2/5. So a slope, is a measure that helps us figure out whether or not a line is rising or falling, and also how steep it is. But in geometry, that's not our only measure for steepness and whether or not something is rising or falling. In geometry, we also use angles to kind of determine that. And so the inclination of a line, if you just plot a line in the plane, the inclination of a line is like eventually, unless that line is perfectly horizontal, eventually that line will cross the x-axis. And so you just measure the angle from the x-axis to the line. So, and it's from the, coming from the right side of the line. So I'm just going to kind of sketch out a couple of different lines here. So I might have a line like this. Its inclination, which we call alpha in these notes, I'm referring to that inclination as alpha. So that line, there's alpha, right? So I'm starting on the right side of the line, moving up to the line, it's that angle right there. A line like this, I'm still starting on the right side of the line, so there's the inclination alpha. The angle alpha could be anywhere from 0 degrees to 180 degrees. And if something has a positive slope, like if we look at the line on the right side here with the positive slope, we can see alpha is an acute angle. And it's only when it becomes like a negative slope that alpha opens up big enough. Those are the obtuse angles. So, if I wanted to, we have these 2 ways to measure how an angle is increasing or decreasing or how steep it is. And we're just going to kind of connect them together. So, let's say I'm going to make one more sketch here, do some stuff in the margins. And for the sake of simplicity, I'm going to draw this line so that it goes through the origin, but it holds regardless if it goes to the origin or not. So there's the inclination alpha. I'm going to draw some perpendiculars. I'm going to drop one down here, and the other perpendicular is just the x-axis here. So we've got this nice right triangle. So if it goes through this point, 0, 0, goes through the origin, and then let's say it goes to this point, x, y, right, whatever it is up there, that means that this distance along the bottom, that horizontal distance, is just x. This distance here is y. We know that the inclination is alpha. We could see here the rise over run is going to be y over x, right? The change in y over the change in x is just y over x, so there's the slope. If we think back to the right triangle trigonometry that we know, SOHCAHTOA, and we use the TOA part, the equation that we get is tan alpha equals y over x, which is what we just observed is the slope of that line. So that's where this equation down here in the box comes from. M equals tan alpha is the equation that relates the slope with inclination. They both measure the same thing, right? There ought to be some equation that relates them together. There it is. And it's really just comes from applying right triangle trigonometry to the triangle that we get when we drop some perpendiculars down in the plane. So in these next examples, in example 1.3, we have a couple of inclinations. They give us a couple inclinations for lines, and we were going to find the slopes. So I'm just going to use that highlighted equation. M is equal to tan alpha. That means M is tan of 45 degrees. Does anybody know what tangent of 45 degrees is? It's 1. Great. 45 degrees is where sine and cosine are equal to each other, so when you take their ratio, we get 1. That's a nice convenient angle. 110 degrees is not as convenient. If we want that inclination, tan of 110 degrees, what do we get? Negative 2.747. So we got a positive slope in part A for that acute angle. Right, this is 45 degrees. This is going to look something like this. And we got a negative slope for the obtuse angle. And that kind of makes sense. That looks something like this. So there's the, 110 degrees. It's going to correspond to a negative slope. There's our acute angle that corresponds to the slope of 1, positive 1. Now we want to go the other direction. So, let's start with the first one, right? So we know they told us that M is 2. And we know that M is equal to tan alpha, so that gives us the equation 2 is equal to tan alpha. If I know what tangent of alpha is, how do we get alpha? Like, how do you get the angle out of the tangent function? So if the tangent is not a factor, tan alpha doesn't mean tangent times alpha. It's tangent of alpha. And so because tangent's a function, we can't actually divide by it. Like the tangent and the alpha are like married in a really close way here that we can't get rid of just by dividing. Any other suggestions? The arctan function, right, or the inverse tan function. So that's how you undo a function in general, is with the inverse function. And these inverse trig functions are the arc functions. So alpha is arctan of 2. And on the calculator, they use like the superscript -1 notation. So you hit the second button and tan. So that superscript -1 tells you it's the arctan or the inverse tan function. Plug in 2 and we get, I get 1.107. So I looked at that number that I got, the type of number that I got there, and I knew right away my calculator is not in degree mode, it's in radian mode. So I'm going to just switch to degree mode here. It's okay to give the answer in radians. Just be aware of what mode your calculator's in. So 63.4 degrees. Now that makes sense. We got an angle that is acute, that corresponds to that positive slope, and that's what we would expect. Now we can use this on the next example, use the same idea. Keep in mind that we know that our inclination is always a positive angle between 0 and 180. So if I start in the same way, right, so negative 0.312 equals tan alpha. And then I say, okay, alpha is going to be arctan of negative 0.312. Let's see what happens. We get an angle of negative 17.32 degrees. And that's problematic for us because we know that the inclination is always a positive angle between 0 and 180. So what we need to understand about the arctan function is that arctan will only give angles over here. And the angles in the first quadrant, it will give you as positive angles from 0 to 90 degrees. But down here, it'll give you negative angles from 0 to negative 90 degrees. Right, and it does that because it wants a nice continuous, like minus 90 to 90 is a nice continuous thing. It will never give you an angle in the second or third quadrant. Arctan is not designed to do that. So what we have to do is adjust our approach here. So we're going to have a second go at this problem. We know that we want an angle, it's a negative slope, so we know that the angle that we're looking for is somewhere in this, in that quadrant. We want that angle, alpha. What we're going to do first, though, is find this angle, which I'll call alpha ref for a reference angle. Notice that alpha ref is an acute angle, right? So basically what I'm going to do is treat this line as though it's in the first quadrant, right? So just sort of flip that over the y-axis. So the alpha reference angle that I want is this first quadrant angle. And the way I'm going to find it is by saying if that red line over there in the first quadrant, that has a positive slope. So I'm going to go over here and say, okay, the positive slope, 0.312, is equal to tan of alpha ref, so that alpha reference is arctan of positive 0.312. This is going to give me a positive acute angle. Of positive 17.3 degrees. And in order to find the angle that I want, the alpha angle that I want, all I need to do is realize that to get to alpha, I'm going to go the full 180 and then just back up by alpha reference degrees. Right? Like that's what we see right here, is if I go the full 180 and then just back up by this measure of 17.3 degrees. So the angle we want in the second quadrant is 180 minus 17.3 degrees. And that's 162.7. Now that jives, right? We expected, we have a line that with a negative slope. Its inclination should be between 90 and 180. How we doing? Questions so far? Are we ready to move on to the next page? All right, so we know we're already familiar with the fact that two lines are parallel if they have the same slope, and if they have the same slope, they'll have the same inclination. We have kind of two competing. I don't know if competing is the right word, but we have these two ideas in mathematics for what it means for two lines to be perpendicular. Geometrically, perpendicular means they meet at 90 degrees. But algebraically, if I have the equations of two lines, the way I see if they're perpendicular is I compare their slopes, right? If their slopes are opposite reciprocal, they're perpendicular to each other. So what we're going to do in this next example is just show that those two things, that if two lines are perpendicular, meaning that they meet at 90 degrees, their slopes must be opposite and reciprocal of each other. Just to kind of jive those two ideas together. So I've got this figure here. We have two perpendicular lines, and our interpretation geometrically is that they meet at 90 degrees, so we know that they meet at 90 degrees there. And I've written down their inclinations. So they have two different inclinations, alpha 1 and alpha 2. We're going to show that their slopes are opposite and reciprocal. So what we're doing here, I'm doing mostly for fun and to kind of just convince us all that these two ideas are I guess, in agreement with each other. If at any point there's a detail that you're not clear on, please stop me. But I think that there's only going to be a couple of times that I might need to remind us of some facts that we learned in trigonometry. So the first thing we want to do here is label some other angles. In particular, this angle right here, you could sort of see that we have a right triangle here, right? Because these two lines meet at 90, and then if the x-axis is another side of that right triangle, we have this little right triangle. So this angle right here in the middle has to be, the two acute angles in a right triangle add up to 90. So that angle has to be 90 degrees minus alpha 1. And that angle, the 90 minus alpha 1, and the alpha 2 angle are supplementary, right? They form a straight line, so they add up to 180. And that means that alpha 2 is 180 minus this angle, 90 minus alpha 1. If we simplify that right side, we find that alpha 2 is 90 degrees plus alpha 1. And now I'm going to rewrite this equation in a way that will be helpful to us to reach our goal. I'm going to solve it for negative alpha 1. So I'm going to subtract alpha 1 and alpha 2 from both sides. So on the left side we have a minus alpha 1. On the right side we have 90 minus alpha 2. These two angles are equal to each other, right? Negative alpha 1 is some angle. 90 minus alpha 2 is some angle. They're equal to each other. And if two angles are equal, then when I take tangent of those angles, they have to still be equal because tangent is a function. So let's do it. Let's take tan of both sides. Right about now, we should be getting the sense that, okay, we're going to make our way to slope pretty soon because now we've got tangent of some inclination angles. We're going to have to remember a few facts from trigonometry. And one of the facts that's going to help us rewrite the left side is that tangent is what we call an odd function. And it's odd, meaning it has symmetry about the origin, or algebraically, when you write it out, tangent of negative of an angle is equal to negative of tan of that angle. It looks like we could just pull out the negative. Now that's not true of functions in general. It's only true if a function is odd. So it's true for tangent, it's true for sine, it's not true for cosine. Cosine's not an odd function. So this is because tangent is an odd function. On the other side, we're going to use another fact about tangent and how it's related to cotan. Now, on the one hand, we know that tangent and cotangent are reciprocals of each other. However, a function and its cofunction, so tan and cotan, or sine and cosine, or secant and cosecant, they're cofunctions because they agree on complements. So tangent of 90 minus alpha 2 is going to be equal to cotangent of the complement. And the complement of 90 minus alpha 2 is alpha 2, right? Like a function and its complement add up to 90 degrees. So tangent of 90 degrees minus alpha 2 is equal to cotan of alpha 2. So cofunctions agree on complements. I'm going to rewrite the right side one more time because cotan and tangent are reciprocals. So minus tan of alpha 1 is equal to, so if cotan's the reciprocal of tangent, that means we could rewrite that right side as 1 over tan of alpha 2. And now we are almost done. Now we're going to be ready to use that connection between slope and inclination. So tan of alpha 1 is the slope of the line with inclination alpha 1. So I guess I'll call it M1. So we have negative M1 is equal to 1 over M2. And we're just about done. Maybe just to kind of button it up and put it in a nice form, I'll multiply both sides by a negative M2. And when I do that, we have M1 times M2 positive is equal to negative 1. And so their slopes are opposite and reciprocal. How's that? Okay. So we've now kind of married the two ideas of what it means for lines to be perpendicular. So if we were, worried about that at all through our mathematical lives, we could kind of put that to rest. We know that if two lines meet at 90 degrees, it forces their slopes to be opposite and reciprocal to each other. Questions about that before we do another example? Okay. All right. So we're going to just finish this section with one more problem with a couple of phases to it. And I think our approach will... I think our approach to this will kind of get us ready for one of the general basic tools that we have in this chapter when we're starting out a problem. So they tell us, they give us 3 points, right? So we have the coordinates of 3 points in the plane. And we want to show that if I connect these points together, that it forms a right triangle, and then we'll find its area. So they give us geometric information, right? In this case, it's points. Like they don't give us algebraic information. They don't tell us, oh, here's the equation of some line or some lines. They just give us this geometric information. They ask us to figure some stuff out. So when I'm doing a problem where they give me geometric information to start with, usually what I do is I start by just plotting the information. So our points are -5, 3, and then 6, 0, and then C is 5, 5. I do this because often when I'm looking at like if I sketch out the information that they give me, they want us to join the line segment, so let's go ahead and do that. If I'm looking at it in the plane, I kind of often have a better idea of how to start. So the first thing they want us to do is show that it forms a right triangle. I guess I have 3 angles here, right? A right triangle, like one of the angles has to be 90 degrees. So I got to just show that one of these angles is 90 degrees. So since we went ahead and sketched it first, I guess there's a pretty obvious choice that we might check first, right? I could go ahead and check all 3 to see which one might be 90, but I think we'd be wise to focus our attentions first on what's going on right at that angle, at angle C, right? That looks like the 90-degree angle, so, I'm going to focus there first. How might I show that that angle is 90 degrees? Yeah, and in fact, rather than find the actual measure of that angle like directly, if I just show that those line segments are perpendicular, meaning we could find their slopes, right, and show that they're opposite and reciprocal, then we'll know that that angle is 90 degrees. So let's find those 2 slopes. So the slope for the line segment AC, y2 minus y1. So I guess I'll call point C the x2, y2, and point A will be x1, y1. So y2 minus y1 is 5 minus 3. x2 minus x1 is 5 minus a -5. So 5 plus 5. And we get 2/10 or 1/5. Positive 1/5. The slope for the line segment BC, I guess I'll keep point C as my x2, y2, and switch point B to my x1, y1. So then we get 5 minus 0. On top, on the bottom, 5 minus 6. So we have 5 over -1, or just -5. Are these lines perpendicular? Yeah, right, so they're different signs, and they're reciprocals of each other. So opposite and reciprocal. So we have a right triangle. Cool. The last thing we want to do is find the area. Now this is a right triangle. Because it's a right triangle, finding the area would be a little bit simpler. If it's a right triangle, then the 2 legs of a right triangle are, you could consider those the base and the height. In order to use the formula 1/2 base height, you know, we have to understand the height is always a perpendicular distance from the base. So if it's a right triangle, we actually get to use the two legs there. So what do we need to find in order to get the area? Yeah, so what are those in this triangle? Say that louder. Great. So we need to find the length of the BC segment and the AC segment. Okay, well, we have a distance formula we can use to find those. So the distance for AC, see, I'm just going to start, here's our formula, x2 minus x1 squared plus y2 minus y1 squared, all in a radical. So I'll continue to treat the point C as the x2, y2. So this is, let's see, 5 minus 3, or that's y2 minus y1. Oh yeah, so 5 minus a negative 5. Plus 5 squared plus y2 minus y1 is 5 minus 3 squared. So we've got, let's see, 10 squared is 100, 2 squared is 4, so we have a radical 104. Now you could, if you want, you know, approximate this, throw it in the calculator, get a decimal. I'm going to just simplify the radical. And if we need a refresher on how we do that, the way we simplify radicals, we always start by factoring. So 104 is 2 times 52, and 52 is 2 times 26, and 26 is 2 times 13. So in a square root, we look for pairs of the same factor, so we could bring one out. So I got a pair of 2's here, and that's the only pair. That once I bring those out as a single 2, I'm out of pairs. So I've got 2 times the radical, and what's left inside is 2 times 13, or 26. Let's do the same thing here for the BC distance. I've already written out the formula right to the left, so I'm going to just jump into to plugging in the coordinates. So x2 minus x1 is 5 minus 6 squared plus y2 minus y1 is 5 minus 0 squared. So 1 squared is 1 plus 5 squared is 25. So we have the square root of 26, which is already simplified. And now that we have these, we can use our formula to find the area. So 1/2 base height is 1/2 times, let's see, 2 root 26 times root 26. So this is going to work out kind of nicely. The 2 and the 1/2 cancel. What's root 26 times root 26? 26. If you had, if you had approximated these distances, and got decimals for the AC and the BC distances, and then multiplied those values together in the calculator, you'd probably get something really close to 26, but a little bit off. You get something approximately equal to 26. Are there questions on this example? Okay. All right. So I think that's as far as I want to get today on new stuff. In class on Wednesday, we will continue on to do the next couple sections in this chapter on the straight line and the circle. And in the meantime, there's some practice exercises you can work on. These aren't to turn into me, but I hope that you will do them. They're well worth your time. Usually, folks who spend time on the practice exercises do, much better on quizzes and tests. A lot of the time what I do when I write up a quiz or a test is I'll just take some problems that were assigned, or maybe just some of the even numbered problems. My goal is that when I write an assessment, there's nothing that would be surprising to anybody who's spent time on the exercises. If you have questions between now and Wednesday, please call or text or email. And, you know what? Actually, one other thing is, if you could, I'm probably going to use Canvas to communicate with the class primarily. So once you have your accounts activated, you can download the app, the Canvas app for students. And when I post an announcement, you'll get like a notification, right? So like, you don't have to worry about having to log in necessarily and checking everything explicitly when there's like a special announcement for the class. And it's the messaging part of Canvas where actually works pretty well. But between now and then, it would be great if you could send me an email so that I can create like a little mailing list in case I need to contact you before you're on Canvas. So maybe send me an email. So that way I'll have your email address, but maybe just tell me one thing you like to do as outside of taking classes. So maybe tell me a hobby or an interest, something a little bit about yourself. I'll get to know you all and get your contact information. Okay. All right, so that's all I've got for you today. I'll see you all on Wednesday. Thank you.